Now I have enough research to write a thorough documentary script. Let me craft part 1. This skill isn't relevant for a text script. Let me write part 1 of the documentary script now. Somewhere beneath the surface of the Pacific Ocean, right now, a mass of water the size of a continent is on the move. It is not a current in the familiar sense. It is not the drift of tides or the slow churn of ocean circulation. It is something else entirely, a pulse of heat travelling eastward through the deep hundreds of meters below the sunlit surface, carrying enough thermal energy to rewrite the weather of an entire planet. Scientists call it a Kelvin wave, and in the spring of 2026, the one moving beneath the tropical Pacific has grown to a scale that has put meteorologists, climate scientists, and emergency planners across the United States on alert. Because when that heat finally rises to the surface, and every model now says it will, the atmospheric consequences for North America will be profound, immediate, and in some places, devastating. Welcome to Sky Space Lab. I am Arthur. This channel is very new, and every like and subscription truly helps us grow and bring you even deeper, more powerful research. Thank you in advance for every like and follow. The storm developing across the United States right now is not a single weather event in the traditional sense. It is not one cyclone forming off a coastline, or one front pushing rain across a region. It is something larger and more complex, a convergence of forces that has been building for months, rooted in changes happening thousands of miles away in the tropical Pacific, yet rapidly expressing itself in the skies above the Great Plains, the Gulf Coast, the Midwest, and beyond. To understand what is coming, and why the next several months represent one of the most consequential weather periods the United States has faced in recent history, we have to begin where all of this actually starts. Beneath the waves, the El Niño Southern Oscillation, known simply as ENSO, is one of the most powerful climate engines on the planet. It is a natural, recurring interaction between the ocean and the atmosphere centered in the tropical Pacific, a slow-motion oscillation that shifts between warm phases and cool phases on a timescale of roughly 2 to 7 years. In its warm phase, known as El Niño, the surface waters of the central and eastern tropical Pacific warm significantly above their long-term average. That warming changes the behavior of the atmosphere above it, altering where tropical rainfall concentrates, disrupting the global circulation of winds, and ultimately bending the jet streams that govern weather across the northern hemisphere. But the event building in 2026 is not a standard El Niño. The data emerging from ocean buoys, satellite sensors, and climate modelling centres in the United States, Europe, and Australia is pointing towards something far more intense. Scientists and forecasters are increasingly using the phrase Super El Niño to describe what may be taking shape beneath the Pacific. The last time events of this magnitude occurred, in 1997 and 1998, global weather patterns were disrupted so severely that floods killed thousands across Latin America, catastrophic droughts spread across Indonesia and Australia, and California was buried under record rainfall. The 2015 to 2016 event caused similarly sweeping chaos, but those events happened against the backdrop of a cooler baseline than today. The oceans are warmer now than at any point in the instrumental record. The atmosphere carries more moisture. The same forcing applied to a hotter world produces a different and more intense outcome. The engine driving all of this is that subsurface Kelvin wave. Understanding what it is helps explain why scientists are paying such close attention. Normally, the Pacific trade winds blow from east to west along the equator, a persistent flow that pushes warm surface water westward toward Asia and Australia, while allowing cooler, deeper water to well up along the coast of South America. This arrangement keeps the eastern Pacific relatively cool and maintains a kind of balance in the atmosphere above. But early in 2026, a pair of tropical cyclones straddled the equator in the western Pacific, causing a brief but powerful reversal in wind direction. Those westerly wind bursts pushed an enormous volume of warm water eastward. That displaced water, with nowhere to go at the surface, sank below and began propagating east as a subsurface pulse of warm water, a Kelvin wave, travelling along the equator at depths between 100 and 300 meters below the surface. A Kelvin wave of this kind typically takes 2 to 3 months to cross the full breadth of the tropical Pacific. As it moves east, it deepens the warm layer of the upper ocean and suppresses the cold upwelling that normally keeps surface temperatures in check near South America. When the wave arrives and begins to rise toward the surface, it effectively turns off the natural cooling mechanism of the eastern Pacific. Sea surface temperatures climb. The atmosphere responds. El Niño locks in. What made the 2026 wave exceptional was its sheer thermal intensity. Satellite data and Argo float measurements recorded anomalies of more than 5 degrees Celsius, roughly 9 degrees Fahrenheit, above average at depths of 100 to 200 meters, figures that place the subsurface heat content at or above the levels seen before the record-breaking events of 1982 to 1983 and 1997 to 1998. Multiple independent modelling systems, including those run by the European Centre for Medium-Range Weather Forecasts, the National Oceanic and Atmospheric Administration in the United States, and the Australian Bureau of Meteorology, have converged on a similar projection. The 2026 El Niño is likely to become one of the strongest on record. Some ensemble members suggest the possibility of surpassing the legendary 1877 to 1878 event, which coincided with catastrophic famine across South Asia, Brazil, and Africa. It is worth being honest here, as the science demands. Forecasting the peak intensity of an ENSO event months in advance is genuinely difficult, and uncertainty remains real. But the trajectory of the data is consistent and alarming in ways that have not gone unnoticed by the people responsible for protecting lives across the United States. I want to pause here and offer something that matters more than any specific forecast. The findings I am sharing with you are drawn from published scientific research, official government agency reports, and peer-reviewed climate studies. But this is a rapidly evolving situation, and the science is updated continuously. I would encourage you, as always, to explore these sources yourself, cross-reference what you hear here with current data from NOAA, NASA, and your own national weather services, and form your own informed picture of what is unfolding. The goal of this channel is to bring you real, grounded information, not alarm without foundation. Now, the question worth exploring is exactly how a warming pool of ocean water, thousands of miles from Kansas or Nebraska, translates into violent storms over those states. The answer lies in the jet stream, and specifically in the way El Niño reshapes that atmospheric river of fast-moving wind at altitude. The jet stream is a narrow band of high-speed winds, typically found between 7 and 12 kilometers above the surface, that flows from west to east across the mid-latitudes of the Northern Hemisphere. It acts as an atmospheric conveyor belt, steering low-pressure systems and storm tracks across entire continents. Its position, speed, and shape at any given time determine where it rains, where it stays dry, where temperatures rise above normal, and where severe weather clusters. During a typical El Niño, the Pacific jet stream is amplified and extended eastward. It strengthens, becomes more consistent in its position, and reaches further into North America than it normally would. The result for the United States is a recognizable pattern. Wetter conditions across the southern tier of the country, from California through the south and into the southeast, more low-pressure systems tracking across those southern latitudes, and a displacement of the polar jet stream toward the north that tends to favor warmer-than-normal winters across the northern plains. But the story for spring and summer, for the period of peak severe weather risk across the central United States, is more nuanced and more dangerous. In spring, the collision zone between the cold, dry air descending from the Rockies and the warm, moisture-laden Gulf air surging northward from the Gulf of Mexico is where supercell thunderstorms and tornadoes are born. That collision has a specific geography, Tornado Alley, stretching from Texas through Oklahoma, Kansas, Nebraska, and into South Dakota. What an amplified El Niño does to this region in late spring is particularly significant. The enhanced Pacific jet stream feeds stronger upper-level winds into the Great Plains, increasing the wind shear that tilts and organizes severe thunderstorms into the rotating supercells capable of producing significant tornadoes. At the same time, the wetter southern pattern means more Gulf moisture available to surge northward. The ingredients for dangerous weather are not just present, they are elevated. The 2026 tornado season began documenting this pattern early. A rapid transition from multi-year La Niña conditions, which had themselves been driving their own weather anomalies, into a rapidly strengthening El Niño created a volatile and unpredictable atmospheric transition zone across North America. Research published in early 2026 examining what scientists called the ENSO phase shift identified this exact transition period as one of elevated severe weather risk for the central United States. The decoupling of what meteorologists call the Walker circulation, the large-scale atmospheric loop connecting the eastern and western Pacific, combined with the downstream impact on jet stream architecture, created conditions ripe for concentrated and intense tornado outbreaks, and they came. By mid-May 2026, the Storm Prediction Center had already documented a season well above normal pace. A multi-day severe weather outbreak centered over Nebraska, Kansas, Iowa, and South Dakota in the third week of May produced over 300 reports of severe weather in a single 24-hour period. Tornadoes touched down near Blue Rapids, Kansas. Homes were destroyed in Nebraska. The Storm Prediction Center issued a moderate risk, its second highest category, for a broad swath of the central United States as conditions aligned for large, long-track tornadoes capable of winds exceeding 110 miles per hour. Meteorologists described the environment in terms that made clear this was not a routine spring setup. Words like volatile and primed appeared in official outlooks. Reports of baseball-sized hail and wind gusts exceeding 80 miles per hour came in from multiple states simultaneously. The Great Lakes region had its own story. A corridor from eastern Iowa through southern Wisconsin and northern Illinois saw a concentration of severe reports that was, by the assessment of National Weather Service offices covering those regions, remarkably active for the period. Early season tornado events in places not traditionally associated with high tornado frequency, including Michigan, reinforced a message that the geographic boundaries of severe weather risk were not static. They were shifting, expanding, responding to changing atmospheric patterns in ways that older preparedness plans had not fully accounted for. To understand why the current storm pattern represents something more than a bad spring, it is worth examining what makes this particular atmospheric moment distinct from other active, severe weather seasons. The United States has seen significant tornado outbreaks before. The outbreak of May 2024 produced 180 confirmed tornadoes over 5 days and caused more than $6 billion in damage. The spring of 2025 was similarly ferocious, with a 3-day outbreak in May generating 133 tornadoes, including maximum rated violent storms with winds estimated near 160 miles per hour. These were devastating events, but they occurred during different background climate conditions, without the additional forcing of a rapidly strengthening Super El Niño accelerating the atmospheric changes driving them. What meteorologists and climate scientists are watching closely now is the compounding effect. The initial wave of severe weather in spring is one layer. The transformation of global circulation patterns as the El Niño intensifies through summer and into fall is another. The forecast implications for winter, 2026 and 2027, when a fully mature Super El Niño would typically exert its strongest influence on North American weather, represent yet a third layer. And underlying all of it is the warmer baseline of the atmosphere and oceans against which this entire event is unfolding. A warmer baseline that does not cause individual storms but does change their character, their intensity, and the amount of moisture they carry. The scale of what is developing above the Pacific right now is not a theoretical projection confined to computer models. It is measurable, observable, and already expressing itself in the day-to-day weather experienced by tens of millions of Americans. The subsurface heat content anomaly in the tropical Pacific captured by the network of Argo floats maintained by NOAA and its international partners was by late spring of 2026 tracking at levels comparable to the months preceding the catastrophic 1997 El Niño. Ocean surface temperatures across the central and eastern Pacific were already showing positive anomalies. Model ensembles from multiple independent forecasting centers were aligning on a peak event expected sometime in the second half of 2026, with impacts on North American weather patterns that would continue well into 2027. For the United States specifically, the forecast signature of a strong to Super El Niño event contains both protective elements and deeply concerning ones. On the protective side, a strong El Niño is historically one of the most reliable suppressors of Atlantic hurricane activity. The same amplified Pacific jet stream that influences severe weather over the plains creates increased vertical wind shear over the Atlantic main development region, the broad expanse of tropical ocean between Africa and the Caribbean, where most Atlantic hurricanes originate and intensify. High wind shear tears apart the organized circulation that a tropical cyclone needs to develop. NOAA's official 2026 hurricane season outlook reflected this dynamic, calling for a below-normal season with a 55% chance of below-normal activity. AccuWeather projected 11 to 16 named storms, below the historical average of 14. Colorado State University's seasonal forecast group similarly projected a quieter than normal Atlantic season. This should not be confused with a hurricane-free season. Climate scientists are careful to emphasize that even a strongly suppressed season can produce significant and damaging storms, because the suppression works at the level of overall seasonal totals, not individual storm behavior. A single, well-organized system can find the gaps in the shear and intensify dramatically. The 2013 season, the quietest in decades, still produced Tropical Storm Andrea and others that brought impacts to the East Coast. And sea surface temperatures in the Atlantic, while not as anomalously warm as in recent record-breaking seasons, remain elevated above historical baselines in ways that can support rapid intensification of any storm that does manage to develop. But for the immediate weeks and months of late spring and early summer 2026, the more pressing and active concern is not the Atlantic. It is the ongoing transformation of weather patterns across the continental interior, driven by that Kelvin wave rising toward the surface of the Pacific and beginning to reshape the atmospheric circulation that governs daily weather from the Rockies to the Mississippi Valley and beyond. The Walker circulation, that large east-west loop of rising and sinking air in the tropical atmosphere, was by late May 2026 showing the early signatures of an El Niño reorganization. The typical pattern of air rising over the warm waters of the western Pacific and sinking over the cooler eastern Pacific was beginning to weaken and reverse. This shift was detectable in the velocity potential analyses run by forecasting centers, which showed anomalies of rising air spreading across the central and eastern tropical Pacific. That rising air and associated tropical convection were already beginning to alter the position and behavior of jet streams in the subtropics and mid-latitudes. For the United States, one of the earliest and most consistent expressions of this shift was increased moisture transport. The southerly jet, that arm of the amplified Pacific jet stream that curves around the base of the subtropical high and delivers Gulf moisture into the interior of the continent, was showing signs of enhancement. More moisture in the low levels of the atmosphere over the plains means more energy available to severe thunderstorms. When that moisture meets the strong upper-level winds and wind shear being generated by the transitioning jet stream pattern, the atmosphere becomes, in the technical language of meteorologists, deeply unstable and highly sheared. Those are precisely the conditions required for supercell thunderstorms and the tornadoes they produce. The atmosphere over the central United States in the spring of 2026 was not simply active. It was operating under a kind of heightened tension, a coiling of meteorological forces that forecasters recognized as something qualitatively different from a normal severe weather season. The jet stream was not just present at altitude, it was running fast, positioned aggressively, and loaded with the kind of directional change with height that meteorologists measure as wind shear and that storm chasers recognize as the invisible architecture of tornado country. When those conditions combine with the warm, humid air that the Gulf of Mexico exports northward each spring, the result is not just bad weather, it is the organized, rotating, violent convection that defines the most dangerous severe weather events in the world. Supercell thunderstorms are, in the vocabulary of atmospheric science, the most structurally complex and dangerous form of convection on Earth. Unlike ordinary thunderstorms, which develop, rain themselves out and dissipate within an hour, a supercell persists. It organizes around a deep, sustained rotating updraft called a mesocyclone, which can reach wind speeds of 100 miles per hour or more even within the cloud itself before a single tornado touches the ground. That rotating updraft is what gives a supercell its longevity and its violence. It can sustain itself for hours, tracking across hundreds of miles of landscape, producing tornadoes, baseball-sized hail, and straight-line winds capable of leveling structures that would survive any ordinary storm. The environment that creates supercells is described by meteorologists using a handful of key parameters. Convective available potential energy, known as CAPE, measures how much energy a rising parcel of air can release as it climbs through the atmosphere. High CAPE values mean explosive vertical development, the kind of updraft that can sustain a mature supercell. Wind shear, both in terms of speed and directional change with height, provides the rotational organization that separates a supercell from an ordinary thunderstorm. Storm relative helicity measures the potential for that rotation to tighten and descend into a tornado. When all three of these parameters are simultaneously elevated, meteorologists describe the atmosphere as primed, and what they mean by that word carries genuine weight. The outbreak of May 16th through 18th, 2026 illustrated this dynamic with brutal clarity. A slow-moving upper-level trough had drifted out of the Rockies and stalled over the plains, creating a persistent region of favourable dynamics that allowed wave after wave of severe weather to develop over multiple days. The warm, moist air flowing northward out of the Gulf was meeting this trough in a way that created an almost continuously active threat zone from Texas northward through Nebraska and into South Dakota. Over 300 reports of severe weather were recorded in the 24 hours surrounding May 17th alone. Tornadoes touched down near multiple towns in Kansas and Nebraska. Homes were destroyed. 2 people were pulled from the rubble of a collapsed structure in Nebraska by first responders. The Storm Prediction Center had issued its moderate risk designation for a broad corridor of states, and the atmosphere delivered on every element of that forecast. What made this outbreak notable was not just its severity, but its character. Several of the tornadoes were described by storm chasers and NWS damage surveyors as showing the behavior associated with significantly sheared environments, long track, relatively narrow, and capable of producing damage well beyond what their width might suggest. One system near Blue Rapids, Kansas, drew multiple simultaneous reports from trained spotters and law enforcement personnel, something that typically indicates a well-organized, persistent tornado rather than a brief spin-up. The Great Lakes corridor that had already been flagged as unusually active through early 2026 continued to generate reports, with a swath from eastern Iowa through southern Wisconsin accumulating tornado and wind damage reports at a rate the Chicago National Weather Service office described as remarkably concentrated for the region. For people living in the affected areas, the experience of these events is something no meteorological summary fully captures. The particular combination of darkness and sound that precedes a violent tornado, the pressure change that many survivors describe as the air being pulled away from them, the silence that falls in the seconds before a supercell's most intense winds arrive, these are things that belong to direct human experience more than to any data set. What the science provides is the framework for understanding why these events happen, where and when they do, and increasingly, for anticipating them with enough lead time to save lives. The improvements in tornado warning time over the past 2 decades, driven by advances in dual polarization radar, better mesoscale analysis tools, and the dedicated work of National Weather Service forecasters and storm spotters, have genuinely reduced tornado fatalities relative to the scale of outbreaks. But the threat itself has not diminished, and in an atmosphere increasingly loaded with the ingredients for severe weather, the frequency and intensity of these events demands serious and sustained attention. The ENSO transition unfolding in 2026 adds a layer of complexity to this picture that extends well beyond any single outbreak. The meteorological community's understanding of how ENSO affects severe weather in the United States has grown considerably in the past 2 decades. Research published in journals including the Bulletin of the American Meteorological Society, Geophysical Research Letters, and the Journal of Climate has established statistically significant relationships between ENSO phase and tornado activity in specific regions of the country and specific seasons. What that research consistently finds is that the ENSO signal on severe weather is not uniform across all of Tornado Alley and not consistent throughout the entire spring season. The relationship is nuanced, regionalized, and dependent on how other atmospheric patterns interact with the ENSO forcing. In general terms, El Niño tends to be associated with increased tornado activity in the southeast and a suppressed or shifted pattern in parts of the traditional Central Plains. But this generalization can mislead because it averages across many events with very different intensities and configurations. A strong or super El Niño introduces additional complexity because it amplifies the jet stream response to a degree that can override the more typical regional patterns. The current event's rapid transition from La Niña conditions, which had been suppressing certain severe weather ingredients to an accelerating warm phase, has created an atmospheric state that does not map neatly onto any single historical analogue. Forecasters are drawing on composite analyses from multiple past El Niño years, identifying the threads of commonality and acknowledging where the current setup diverges from all of them. This is, at its core, the challenge of weather and climate science in a period of rapid change. The historical record, which provides the foundation for probabilistic forecasting, was assembled during a period of greater atmospheric stability than the one we now inhabit. Climate patterns that took decades or centuries to develop are shifting, and the models built from that historical record must be continuously updated to reflect a changing baseline. NOAA's research divisions, NASA's Earth science programs, and university climate departments across the country are all grappling with this problem simultaneously, trying to understand how a hotter, more energetic atmosphere will express itself through the familiar mechanisms of severe weather, while also generating new behaviours and intensities that the historical record may not adequately capture. The 2026 severe weather season, still unfolding, sits at this intersection. It is recognisable in many ways. The same dynamics that have produced tornado outbreaks on the plains for as long as humans have recorded them are present and active. The geography of risk has not relocated. The physics of supercell formation has not changed. But the intensity of the forcing, the depth of the moisture, the speed of the jet stream at altitude, and the energy available in a warmer baseline atmosphere are all elevated in ways that correspond to the signal expected from a rapidly strengthening Super El Niño operating against the backdrop of a changed climate. The Weather Prediction Center's Storm Summary Archive for 2026 already reflects a year of unusual activity across multiple storm types. February saw a major nor'easter that dropped nearly 38 inches of snow at Green Airport in Rhode Island and produced hurricane-force gusts exceeding 95 miles per hour at Wellfleet, Massachusetts. That blizzard caused 30 fatalities and knocked out power to more than 600,000 homes and businesses across the Northeast Corridor. March brought another significant blizzard from the High Plains to the Great Lakes. April produced a late-season winter storm in the north-central United States, at a time when the atmosphere was simultaneously destabilizing for spring severe weather further south. By May, the pattern had fully shifted into warm season mode, and the severe weather machine had come to life across the plains with an intensity that left communities from Nebraska to Ohio calculating damage and conducting damage surveys. This compressed sequence of major events across different storm types is itself a fingerprint of the ENSO transition. The same atmospheric reorganization that drives a powerful El Niño into being tends to produce, during the transition phase, a kind of meteorological whiplash, cold air outbreaks and late-season winter storms in one region, while spring-like instability and severe weather develop in another. The atmosphere is, in a real sense, reorganizing itself, finding its new configuration under a different set of boundary conditions, and the weather produced during that reorganization can be particularly difficult to anticipate with precision. It is a reminder that it is worth independently verifying any specific forecast you rely on for safety purposes, whether that is from this channel, from news media, or from any other source. The National Weather Service and your local emergency management office are the authoritative sources for the warnings and watches that protect lives. As the Kelvin wave that has been travelling eastward beneath the Pacific surface continues its journey and begins to express itself in rising sea surface temperatures, the atmospheric response is accelerating. Fox weather meteorologists noted in mid-May 2026 that the transition to what they described as a Super El Niño climate pattern was accelerating faster than earlier projections had suggested. The southern tier of the United States, from California through the southwest, Texas, the deep south, and into the southeast, is expected to experience a wetter-than-average pattern through the second half of 2026 and into the winter months. The Pacific jet stream, amplified and shifted southward, will act as what Fox Weather's analysis called an atmospheric conveyor belt for storms, delivering precipitation systems across the lower 48 with greater frequency and intensity than what has been typical in recent years. For California, which spent the preceding La Niña years grappling with drought conditions in many regions, a strong El Niño carries the prospect of relief through atmospheric river events, those narrow corridors of concentrated moisture flowing in from the Pacific. But the same events that replenish reservoirs and snowpack can also produce landslides, flash flooding, and infrastructure damage when they arrive in rapid succession without adequate time for soil absorption between storms. The California experience during the 2022 and 2023 El Niño-influenced winters demonstrated this dynamic acutely, as a parade of atmospheric rivers brought both relief from drought and catastrophic flooding to communities in the Central Valley and foothill regions. A stronger event carries both greater benefits and greater risks. For the Gulf Coast and the Southeast, the El Niño pattern tends to increase the threat of winter tornadoes and severe weather, a phenomenon that catches many residents off guard because the seasonal association of tornadoes with spring can create a false sense of security during winter months. El Niño winters historically favor more frequent intrusions of warm, moist Gulf air even during December and January, and when those intrusions collide with cold fronts, tornado-producing supercells can develop at times of year when few people are monitoring their weather alert devices. The southeast's vulnerability to winter and early spring tornadoes is well established in the climatological record, and a strong El Niño reinforces this risk. The broader planetary context of what is unfolding deserves careful consideration. The Kelvin wave driving the 2026 El Niño developed against the backdrop of ocean temperatures that are, by satellite measurement, the warmest in the instrumental record across large portions of the global ocean. This is not a cyclical fluctuation within a stable system. It is a fluctuation within a system that has itself been shifting, driven by the accumulation of greenhouse gases that retain more of the sun's energy within the Earth's climate system. The interaction between natural climate variability, of which ENSO is one of the most powerful expressions, and the human-forced changes to the baseline state of the atmosphere and ocean, is an area of active and genuinely unsettled scientific investigation. What climate scientists can say with confidence is that the same amount of ENSO forcing, applied to a warmer baseline, tends to produce more intense precipitation events, more severe flooding, and in some cases more intense storm systems. This is a physical consequence of the fact that a warmer atmosphere holds more water vapor, roughly 7% more for every degree Celsius of warming, and that additional moisture amplifies the rainfall and snowfall associated with any given storm system. It also increases the energy available in severe thunderstorm environments, raising the ceiling on storm intensity. These effects are not speculative. They are grounded in fundamental thermodynamics and supported by the observational record of recent decades, which shows a consistent increase in the frequency of extreme precipitation events across much of the United States. The summer forecast for the United States, shaped by the accelerating El Niño signal, carries several additional dimensions worth understanding. The pressure pattern associated with El Niño summers historically tends to place a broad low-pressure tendency over parts of the eastern United States, which can keep temperatures more controlled than they might otherwise be in the northeast and mid-Atlantic. The amplified Pacific jet stream, stretching its reach across the continent, can also play a moderating role on summer heat extremes in the northern tier. But this same pattern, combined with enhanced moisture delivery from the Gulf, creates the conditions for persistent and active thunderstorm development across the interior of the country through the summer months, well past the traditional peak of tornado season in May and into June, July, and even August. The concept of an expanding severe weather season, one that does not simply peak in May and fade rapidly through summer, is something that climatologists have been tracking as a long-term trend for several years. Research published by scientists at institutions including the National Severe Storms Laboratory and the University of Oklahoma has documented a statistical elongation of the severe weather season, with significant tornado and severe thunderstorm activity occurring more frequently outside the traditional spring peak window. The causes are multiple and interacting: changes in the position and behavior of the jet stream, shifts in the timing of moisture availability from the Gulf, and alterations in the frequency of the synoptic scale setups that organize severe weather outbreaks. The 2026 El Niño is expected to amplify these tendencies, creating a summer and early fall characterized by recurring severe weather threats across the central and eastern United States. The National Hurricane Center's tropical weather outlook for late May 2026 showed no tropical cyclone development expected in the Atlantic over the following 7 days, consistent with the early season suppression typical of a strengthening El Niño. But the absence of tropical storms in the immediate term does not mean the hurricane season will be irrelevant to the overall picture. The Atlantic season officially begins on June 1st, and even in suppressed years, several named storms typically develop. The key question for coastal communities from Texas to Maine is not whether any storms will form, but whether any of those that do form will encounter the atmospheric cracks in the El Niño's wind shear defense and manage to intensify before approaching land. The 2013 Atlantic season, one of the quietest on record with only 2 hurricanes, is sometimes invoked as reassurance that an El Niño year means safety from hurricanes. But 2013 produced several storms that caused significant impacts, and the confidence that a below-normal season will remain without dangerous landfalls is misplaced. NOAA itself was explicit in its 2026 outlook that even in a below-normal season, direct impacts on the United States are possible, noting that 3 to 5 direct impacts on the United States were forecast throughout the season. A direct impact in the official meteorological definition includes effects from storms that do not make landfall but pass close enough to drive dangerous storm surge, rainfall and wind into coastal areas. The infrastructure of storm forecasting and warning in the United States has never been more sophisticated. NOAA's 2026 hurricane season preparations included the integration of drone data into hurricane forecast models for the first time, a partnership with Black Swift Technologies that provided a fleet of uncrewed aircraft capable of collecting data in extreme weather conditions. The data collected by these drones, feeding into NOAA's forecast model suite, represents a meaningful addition to the observational foundation on which intensity forecasts are built. Intensity forecasting, the prediction of how fast a tropical storm will strengthen, has historically been the hardest problem in operational hurricane meteorology, lagging decades behind track forecasting in its accuracy. Any improvement in the ability to predict rapid intensification, the explosive strengthening that has characterized several recent hurricanes in their final hours before landfall, has direct life safety implications. NOAA also implemented an improved version of the Tropical Cyclone Forecast Cone graphic for 2026, one that now includes tropical storm and hurricane watches and warnings for inland areas of the continental United States, Hawaii, Puerto Rico, and the US Virgin Islands. This change reflects a hard lesson learned from past events, where the narrow focus on coastal impacts left interior communities unprepared for the catastrophic inland flooding that some tropical systems produce. Hurricane Harvey's 2017 devastation of Houston was driven not by wind but by extraordinary rainfall, more than 60 inches in some locations, delivered by a storm that sat nearly stationary over southeast Texas for days. The expanded warning graphic is a recognition that the danger from tropical systems extends far beyond the traditional wind zones and storm surge threat areas. The machine learning tools being applied to quality control radar data from NOAA's Hurricane Hunter aircraft represent another dimension of the technological evolution in weather forecasting. Hurricane Hunters, the WP-3D Orion aircraft, flown directly into tropical storms and hurricanes by NOAA's Aircraft Operations Center, collect some of the most critical observational data in all of meteorology. The tail Doppler radar mounted on these aircraft provides three-dimensional wind structure information from within the storm that no satellite or ground-based radar can replicate. NOAA's Atlantic Oceanographic and Meteorological Laboratory reported that the new machine learning approach to quality control of this data captures more than 25% additional meteorological data compared to the previous method, providing more complete and accurate information about storm structure and wind distribution. All of these tools, the improved models, the drone data, the enhanced radar processing, the expanded warning products, exist in service of a single fundamental goal: giving people enough time to get out of the way. The warnings work. The research consistently shows that tornado warning lead times have extended significantly over the past quarter century, and that those extended lead times save lives. The challenge is not purely technological, it is also social and behavioral. People who receive warnings do not always act on them, for reasons that range from warning fatigue to misunderstanding of the risk to practical barriers to evacuation or sheltering. Emergency managers and social scientists have spent years studying the communication of weather risk, trying to understand how to reach the people who need to hear the message most clearly and move them toward protective action. The storm that is developing across the United States in 2026 is, in its broadest sense, a story about the interaction of natural climate forces with a changed atmospheric state, and about the human systems that exist to anticipate, communicate, and respond to the consequences. The oceanic Kelvin wave that lit the fuse of this year's ENSO event was itself triggered by tropical cyclones and windbursts that were, in turn, shaped by ocean temperatures elevated above their historical baselines. The severe weather outbreaks of spring 2026, the tornadoes in Nebraska and Kansas, the hail and wind reports across the Midwest, the abnormally active severe weather corridor across the Great Lakes, are all downstream expressions of a cascade of atmospheric cause and effect that began beneath the surface of the Pacific months earlier. Understanding that cascade does not make the destroyed house in Nebraska any less destroyed, or the family who sheltered in their basement any less frightened. But it provides something essential, a framework for anticipating what comes next, for allocating resources and attention where the science says they are most needed, and for making the decisions, both individual and collective, that determine how prepared any given community is when the next severe weather threat materializes. The weeks and months ahead carry genuine uncertainty alongside real concern. The El Niño is still intensifying. Its peak atmospheric expression, when it typically exerts its most powerful influence on North American weather patterns, is expected in the second half of 2026 and potentially into the 2026 to 2027 winter season. The Atlantic hurricane season that officially opens on June 1st will unfold against a backdrop of suppressed large-scale conditions but elevated baseline ocean temperatures. The severe weather machine across the central United States will continue to find fuel in the moisture and instability that a transitioning atmosphere delivers, and the infrastructure of American communities, from coastal cities to plains farming towns, will face the test of an active meteorological period with consequences measured in lives, in livelihoods, and in the accumulated damage that extreme weather extracts from the built environment. The scientists at NOAA, NASA, and the European Centre for Medium-Range Weather Forecasts are watching the same data the public can access, but with tools and analytical frameworks that allow them to see into the structure of what is unfolding with greater precision. Their message, translated into accessible language, is consistent. This is a year to pay close attention, to be prepared rather than reactive, and to take seriously the warnings and outlooks issued by the institutions whose entire purpose is to read the atmosphere accurately and communicate what it is telling us. The oceanic pulse that began this story, that subsurface Kelvin wave moving east through the tropical Pacific, is still travelling. Its energy has not yet fully expressed itself in the atmosphere above. What it will produce as it continues to surface, as the El Niño it is driving intensifies toward its expected peak, will shape the weather of the United States and much of the world for the next year, and possibly beyond. The storm developing fast is not only the ones already crossing radar screens over the plains, it is the one still building, thousands of meters below the surface of an ocean most Americans will never see, gathering the heat that will one day arrive above their heads.